So let's get started. Hi everyone, this is Yuchen. So today I will present our paper in ECCV, which is follow the rules, reasoning for video anomaly detection with large language models. And today my talk will be around 30 minutes, and feel free to ask any questions if you have. Okay, so video anomaly detection is a challenging task, and one of the main reasons for this difficulty is that what an abnormal event looks like depends on the context. So for instance, consider a truck driving on the street. This is completely normal in most settings, but now imagine the same truck driving through a pedestrian-only area. In this context, it becomes an abnormal event that could signal a potential issue. And similarly, take the example of a person jogging. So this is a perfectly normal activity in a park or on the sidewalk. But if someone is seen running outside of the bank, the context changes, and it might indicate an emergency or suspicious behavior. And this makes abnormal event detection a highly complex task because it depends on where and when it occurs. So it requiring systems that go beyond recognizing patterns to actually understanding the environment and its norms. So video anomaly detection can be applied to a wide range of potential applications. For example, it can be used to identify the rare events and understand the unexpected behavior. And also it could be used to improve the safety, like to to show like how to react to the detected anomalies. And also it can be used to enhance the data diversity, like to collect more diverse and representative data sets. And also it could use for predictive maintenance. So let's start it by understanding the classic setting for one-class video anomaly detection. And in this setting, it's hard to collect abnormal examples, which makes the supervised learning method impractical since we do not have that much labeled anomaly data sets for training. Instead, this assumption relies on a key idea that the abnormal events are unexpected and occurs far less frequently than the normal events. So this means the normal events, which are common and familiar to us, can be easily collected and used for training. So this is why it names at one class VAD, because it only used the one class normal data sets for training. And with this setup, video anomaly detection is also often formalized as an outlier detection problem. Well, the goal is to identify events that deviate significantly from the normal patterns learned during the training. And this approach allows us to detect anomalies without requiring the labeled examples of every possible abnormal events. So the traditional video anomaly detection usually relies on the full shot training mechanism, where the entire video data set is used to learn patterns of the normal behavior. For example, the widely used Shanghai Tech datasets consists of near 300,000 frames specifically for training. However, while this approach is effective, it can be computational intensive and may not generalize well to the unseen scenario or background, especially if the training set doesn't fully capture the variety of the normal events. And another problem is they only output the anomaly score here without any rationale, which means they do not have the explainability for the decision making it hard to understand why a particular event is classified as anomalies. So this hinders them from earning public trust when developing in real-world products, because the user may eager to know or may interested to know that what is the reason behind the model's decision making. So when nature thinking about when we talk about the reasoning or rationale is the LLM or VLMs. So can we leverage the LLM or VLM to achieve the zero-shot video anomaly detection with a human-friendly rationale? So this is the problem we want to explore in this paper. So let's see what happened if we ask GPT-4V directly. So for instance, here we feed a task frame which is a ground truth abnormal, and we ask GPT-4V, is this frame normal or anomaly? And here GPT-4V mistakenly treats skateboarding as normal, because in a general context, skateboarding is indeed a normal activity. But in the specific context of, say, a restricted area only for pedestrians, or in those benchmarks data sets, the skateboarding could be considered anomalous behavior. And this example highlights a key challenge. So the language model or vision language model is trained on various of data sets and with the like common knowledge, and it may not recognize anomalies that are context specific because it does not account for the particular environment or rules of a given setting. So what do we want from a better video anomaly detection system? We want to extract some rules that define normal and anomalous behavior. For example, these rules could indicate that skateboarding is considered an anomaly in specific VAD scenario, such as inside a pedestrian-only area or a shopping mall. And these rules can also help us not only understand why certain events are classified as anomaly, but also enable us to effectively detect the unseen anomalies. So how do we achieve it without fine-tuning? We propose to utilize the rule-based reasoning, which include two important stages, which is the induction stage and also the deduction stage. So in the induction stage, we want the model to learn rules from the few-shot normal reference frame. So this is to mimic the one-class training procedures in the traditional VAD tasks. And here, the few-shot normal reference phrase means we randomly sample several frames from the training set, which are all normal frames. And then we use this normal frames to derive some rules and summarize the patterns for the normal behaviors, and we will get rules for normal. And then based on these rules for normal, we use the reasoning ability to let the language model to derive rules for anomaly. And so this is the induction stage. The goal is to derive the rules. And this is no training needed in the entire process. And for the deduction stage, which is to mimic the testing stages in the traditional VAD tasks, so we use this rules derived from the induction stage and to detect anomalies based on the rules. Like for example, this should be the this is the deduction results for the specific test frame, and the answer will describe what are people doing in these images, and beside the people there are what are other like environmental objects, and which activities falls into the anomaly rules and thus lead to anomaly detection results. So here is a set of rules induced from the Shanghai data sets. So we will have rules for normal human activities and rules for environmental objects, and also rules for anomaly human activities and rules for anomaly environmental objects. So for the normal activities, there are basically activities like walking or standing or sitting, such as this. And as a comparison, the anomaly human activities will be like running and non-walking movement or aggressive or unusual movement. Yeah, so we will have those set of rules for use for deduction. And this is another set of rules. So the content are quite similar, but the format are different, since the rules is generated by the induction stage is based on GPT-4. So the answer will be different, like for different queries. So how do we get these rules and effectively use the rules? So this is the pipeline of our method. We have 6 modules here. So the above line is the induction stage, and the bottom line is the deduction stage. So in the induction stage, we will have 3 modules. The visual perception, which take responsibility to transfer the image frame into the text, and then the rule generation, and then rule aggregation. And in the deduction, also we have the visual perception and perception smoothing to mitigate some errors, and also the robust reasoning to get the rationale. So among the 6 modules, the rule aggregation and perception smoothing and robust reasoning are the modules designed to enhance the system's robustness and help it achieve the state-of-the-art VAD performance. So let's take a look at each module one by one. So first is the visual perception. So here, so in the induction stage, we will first randomly sample several reference frame from the normal training data sets. And in our experiments, 10 to 20 frames is enough to generate a set of rules to achieve the state-of-the-art performance. So it is like quite efficient. So here we will input the prompt and also like the several frames here, and we will separate the human and environment objects, which can help VLM to pay attention separately to the environmental elements and the human activities. And the output will be the frame description. For example, for this frame, the output will be there are 4 people in the images, and it will describe each of them is doing blah, blah, blah. And also, other than people, there will be trees, path, bridge, some like background information. And in the visual perception stage, we are using an open source VLM named CockVLM. And then after we get the those frame descriptions, we will let the language model to generate the rule. Here in our experiments, we're using the GPT-4 in this stage, since we only like needs 10 to 20 frames, and that's the query is not that much. So we use GPT-4V here. And the input would be the description we got from the last step, and also the prompt here. Here we also have several strategies for the prompt. So first we separate the normal and anomaly. So basically we first we first let the model to derive the rules for normal based on the frame description. And then we, like for example, if walking is a common pattern in the description, it will becomes a normal rule. And then we will do a contrast, which is compare the normal rules, let the model to derive potential rules for anomaly. And compared with walking, the non-working movement will be included in the rules for anomaly. And so the second strategy is the abstract and concrete. So we ask the model to start from the abstract concept and then generalize to concrete human activities or environmental objects. So for example, walking, whether alone or with others, or non-working, such as riding a bicycle, scooting, or skateboarding. So we hope to leverage the analogy here to help the model to bridge the gap between the abstract concepts and the unsaying concrete examples. For example, in this example, there is no running listed here, but we hope that the non-working movement can be a context to help the model to handle the unsaying concrete examples. And the third one is human and environment. So this is the same as the visual perception. We try to lead the language model to pay attention separately to the human and environmental. Thus can help it to do the reasoning easily. So now we will have a bunch of rules. Oh, I forgot to mention that in the previous step, since we have referenced like we have sampled different independently like different set of frames, and for each set of frames, we will derive a set of rules. And then in this rule aggregation stage, we will aggregate those rules into a final one set of rules used for deduction. And the reason is to mitigate the errors in the previous step. Here is the prompt we used for aggregate the rules. And the high level idea is to mitigate the errors from the previous stage, such as the visual perception modules, potentially misinterpretation of walking and as skateboarding. So this will lead to incorrect rules. For example, the skateboarding might be considered as normal rules. So this is absolutely what we do not want. So we use this rule aggregation to try to mitigate those errors. And the idea is that the errors may occur on a single input, but are less likely to consistent occur across many randomly sampled inputs. So this is the assumption under randomized smoothing. And by doing this, we do the majority vote to filters out the uncommon elements by retaining the rule elements consistent present across different randomly select sets. So now we will have like these rules. So we will use these rules in the deduction stage to do the reasoning and to do the detection. So the first module of the deduction is also the visual perception, and it is exactly the same as the induction stage. The only difference is the input is continuous frame from each video in the task sets. So this set will contains both normal frames and anomaly frames in a sequence. Here is an example of two test frames. The first one is an abnormal frames, and the second one is a normal frame. So this is the description for the abnormal abnormal frame. It will say one person is working, another is working, and third person is riding a bicycle, and fourth person is riding near the is walking near the bicycle. And for the normal frames, and it will also give the description like one person working and another person also working, and other than people, there are what environment objects, blah blah blah, and after we got this frame descriptions, we will do a perception smoothing because there might be, as we mentioned before, there might be errors happens in the perception stage, and we try to mitigate it. So the goal is to correct the errors in the visual perception. For example, an image showing someone running might be mistakenly perceived as walking, and such misclassification can lead to false negatives in the anomaly detection. And the idea is that the movements are continuous and should be consistent over time. So based on this idea, we designed the perception smoothing contains 3 steps. So the first step is an initial labeling via the rule matching. Here we use the keyword matching, which is to check if the description contains the keyword listed in the anomaly rules, especially the ing verb as human activities. And the second step is exponential majority smoothing. So we perform an EM. So the first step of the exponential majority smoothing is exponential moving average. And we do this step on each original frame in the video clip. This means we will calculate the EMA value to consider the trends from the previous frame and smooth out fluctuations in the prediction values. And here, alpha as a parameter that influence how much weight we give to the recent data points in the EMA calculation. And the second step is to do a majority vote. So we will look at a window centered around the current frame with a padding size P. And within this window, we consider its neighboring values and determine the final smooth prediction based on whether the majority of these values are above or below a certain threshold. And this helps us consider the trends from the neighboring frames and enhance the consistency of our prediction. So yeah, so the basic idea of the exponential majority smoothing is first, align with the trends from the previous frame, and second, align with the trends from the neighboring frames. After doing the prediction smooth, we will modify the description. So the modification is following its neighbor's majority within a window size. Like for example, if your neighbors are all containing like running, but you do not, so we will correct this to follow the majority of the neighbors. Okay, so the final module is the robust reasoning. So instead of directly ask the language model to analyze the description, we add a double check strategy here. So showing us this example, the prompt would be so my dummy answer is what we got from the last step, which is the smooth prediction. And we will use this dummy answer as a hint and to let the model double check if our answers is correct or not, which is based on the modified frame description and on the rules we got from the induction stage. And we find this can help the decision making and helps our system reduce the missed anomalies and helps the reasoning more closely align with the rules. So this is the output for the previously two two examples. So the first one is the answer is anomaly, because the bicycle match rule number 2 under the anomaly environmental objects. And also the second one is an example of the normal, and it will say we find walking, and walking is under the normal rules, and also the environmental objects are all under the normal rules. So the final answer will be normal. So what is the performance of this system? So here is the choice of our language models and the vision language models. So for the visual perception, we use an open source called VLM because we need to test on the full set data sets, which is a large scale test. And if you use GPT-4 will cost too much for the experiments. And also the robust reasoning in the deduction stage, we also use a open source mixtural language model. And in the rule deduction, we use GPT-4 because it only needs to test like 10 to 20 samples. And we find that GPT-4 indeed have the best performance in the rule deduction in the rule induction stage. So we choose the GPT-4 here. And we also test other combinations of the open source or closed source model. And finally, we choose the best consideration of CogVLM plus Mixtral. So this is the detection result compared with the state-of-the-art VAD. And we can say that on the two most challenged data sets, which is Shanghai Tech and UB normal, we perform pretty good, and it's the performance is aligned with the best state-of-the-art. It's the similar to the state-of-the-art results. And interestingly, and we find our framework also works well on the cross-domain detection, video anomaly detection. So cross-domain VAD means the training, or in our case, the induction stage is doing on a target data sets, and the testing or in our scenario, the deduction is doing on another data sets. So here for Path2 Avenue and UB normal, our target source is Shanghai Tech, which means we use the rules generated from the Shanghai Tech data sets and then test on the other data sets. So we think the advantage is due to the high-level abstraction of the language compared with the complexity of high-dimensional visual features. So for example, the word running might be straightforward in text, but the visual representation is far more complex. And if you change the weather condition, or if you change the background information, the model might not be able to correctly output the running as the from the visual perception. And also we think it is benefit from the overlap of the anomaly concepts across the data sets, like Path2 Avenue and Shanghai Tech. Yeah, so for the UB normal, for the UB normal, the anomaly is more diverse. So we can say that there is a performance drop for the UB normal data sets. And also we have tested the reasoning performance versus VAD using language models. And this is the example of how we conduct the test. So for each frame description, we design like 4 choices for reasoning evaluation. So we have 3 abnormal and 1 normal. So for the abnormal, we will have 1 correct choice with the correct reasoning, but the others is the others reasonings are wrong. So this is the doubly right, the right detection and also the right reasoning. So this is the results of the 100 randomly selected frames from the Shanghai data sets. And we can see that compared with the baselines, anomaly ruler, which is our work, performs pretty good. And on the conclusion part, so we propose the first reasoning approach for one class VAD, and also the proposed method is a novel field normal shot prompting approach without any training and without fine tuning, and enables fast adaptation to various VAD scenarios. And also we propose the rule aggregation, perception smoothing, and robust reasoning strategies to enhance the robustness and leading to the state-of-the-art performance. And also our work is open source at this link. Feel free to check it out if you are interested. Thank you.
All right, so it does look like we have one question in the Q&A, which you may or may not have covered, and it has to do with synthetic data. I can read it out for you. For lack of data for training for detecting visual anomalies, can you attempt to utilize data synthesis for those edge cases specifically? This was very early in the presentation.
For training. Oh, you mean so in the VAD so let me so do you mean that in the video anomaly detection tasks, because there is like absence of the abnormal examples, so traditional methods are basically focused on the one class VAD, and this question are asking that if the data synthesis can help, like can help to generate some anomaly data and use for supervised training. So am I understanding this correctly?
So Guy, if you want to repost your question or just acknowledge that that covered it, that would be great.
Okay.
It sounds like that covered it. So fantastic. And then we do have a question that came into the chat, not the Q&A, but the question is, what are the practical use cases for the anomaly ruler justifying fees to use Chat GPT-4?
Let me, what are the practical use case for the anomaly justifying fees to use ChatGPT-4? Do you mean how much the anomaly ruler will be cost, like using using GPT?
My sense is that's what the question is aiming at.
Okay. So as I mentioned in, let me jump to the slides. So as I mentioned in this slides, so in the rule induction stage, so we only use the rule GPT-4 in the rule induction oh, what applications are valuable enough for paying the fees. So we only use the GPT-4 in the rule induction stage, which needs like 10 to 20 queries. I think less than $1 is enough for the rule induction stage. And for the deduction stage, that needs to iteratively cover all the testing sample. We use the open source models without charge. Yeah.
And then I think we do have one final question in the Q&A, which is related to training and fine tuning. Did you fine tune model for reasoning? I guess
No, so I did not fine tune the model for reasoning. So this is a totally zero shot approach. Yeah.
All right. Well, okay. So one last question here. Did you make use of multi-agents for the rule detection reasoning module?
Multi agents for the rule deduction reasoning module. Oh, I think I don't use, so I think in the row deduction we only use the model is mixture 8B, if I remember correctly, and it is like only like language agent.